You know, the future of semiconductors isn't just about shrinking things down anymore. The real cutting edge is about making chips smarter, and we do that by combining totally different materials on a single device. It's called heterogeneous integration. And the key to this whole revolution? It's a process called wafer bonding. But there's a massive, and I mean invisible challenge that's holding it all back, a problem happening at a scale that's almost impossible to comprehend. Just think about that for a second. What if the single greatest roadblock to building the next generation of RF power and photonics is something you literally can't see? It's a threat hiding in plain sight, right there at the atomic level. So here's how we're going to tackle this. First, we'll look at the incredible promise of this integration. Then we'll pull back the curtain on that invisible barrier I mentioned. After that, we'll get into the nitty-gritty of the technical fallout and what it means for the business bottom line, before finally exploring a brand new way to solve this whole problem. For decades, everyone lived and breathed Moore's law. But let's be honest, we're in the more than Moore era now. The real leaps in innovation are coming from bonding wildly different materials together. Think gallium nitride on top of silicon. This is how we unlock performance levels that were just a fantasy with a single material. And wafer bonding, well, it's the absolute cornerstone making all of this reality. It's the enabling technology. But this incredible process is slamming into a fundamental bottleneck, right where those two wafers are supposed to meet, down at the atomic level. And here it is. This is that invisible barrier. We are talking about defects in contamination so unbelievably small, they make a single nanometer look huge. These are the insidious little threats that can undermine the entire multi-billion-dollar process. So what exactly are we up against here? We're talking about things like tiny dislocations in the crystal lattice, dangling atomic bonds that have nothing to connect to, and microscopic leftovers, stray organic molecules, or worse, oxides. These are the culprits because they physically prevent the two wafer surfaces from making that perfect seamless connection. Now, this is the part that is just mind-blowing. This process is so incredibly sensitive that a single layer of oxide atoms, just one atom thick, is all it takes to completely ruin the bond. That's the margin for error we're working with here. It's basically zero. So what happens when these invisible gremlins get in the way? Well, the fallout is huge, and it's very, very real. It creates this awful domino effect that hits absolutely everything: device performance, long-term reliability, and of course, manufacturing yield. This chart really connects the dots from the atomic flaw to the real-world headache. On the performance side, these defects act like traps, slowing everything down. That means lower switching speeds in your HBTs and MEHTs. For reliability, those tiny voids can grow under stress, creating dangerous hotspots and drastically shortening the device's lifetime. And then there's the big one: manufacturing yield. The worst part is, you often don't catch these failures until way late in testing, which leads to just brutal scrap rates and a soaring cost for every good die. And of course, that brings us to the money. All of these deep technical problems, they don't stay in the lab. They translate directly into massive financial pain. We're now moving from the scale of nanometers to the scale of dollars. I mean, look at the industry. We're pouring billions upon billions of dollars into new fabs. When your yields are in the tank because of these interface issues, you're not just losing product. You are actively eroding that monumental investment. Every single wafer you have to scrap is just wasted capital. This little graphic perfectly shows the chain reaction. It all starts with a poor quality interface at the atomic level. That leads directly to high scrap rates. That, in turn, delays your R&D, pushes back your time to market. And worst of all, if a bad device gets out into the world, you're risking serious long-term damage to your brand. It's a microscopic problem with truly macroscopic consequences. What this all means is that the old way of thinking just isn't going to cut it anymore. It's no longer good enough to just manage or try to work around these defects. To win, to actually stay competitive, the industry has to shift its focus to eliminating them right at the source, before the bond is even made. And that's where a new path forward starts to open up. We're not talking about a small, incremental improvement here. We're talking about a completely new paradigm for how we prep wafer surfaces, a way to achieve a genuinely perfect interface. This slide really says it all. You've got the old way on the left, conventional stuff like wet cleaning and plasma activation. That stuff just manages the surface contaminants. But on the right, that's the new way: atomic level purification inside an ultra-high vacuum. This isn't just about cleaning. This is about eliminating contaminants that are deep-seated and, get this, actually healing the crystal lattice of the surface before the wafers ever touch. And this is where technologies like SisuSemi's atomic-level purification are changing the game. They deliver 3 critical outcomes. First, true covalent fusion, creating a bond so strong it's like a single perfect crystal. Second, a massively reduced interface state density, or DIT, which means maximum electrical performance. And third, uniformity at scale, so you get that same perfect result across an entire 300mm wafer. You know, this quote really brings it all home. As we push the boundaries of AI, of 5G, of electric vehicles, the real innovation, the next big leap, is all happening right there, at the atomic scale. The interface isn't just some place where 2 things are stuck together anymore. It is the new battlefield for performance. Mastering that battlefield is exactly what's going to separate the leaders from the laggards in the years ahead. For anyone who wants to go deeper on this, I'd really encourage you to check out SisuSemi.com.